week's training. Whether you're joining us from around the world or here locally at the Emergency Reporting Training Facility and corporate headquarters in Bellingham, Washington. Just want to say welcome to people who have RSVP'd as yes for attending this. People from Reno, Nevada, Warren, Michigan, Blaine, Washington, Riverview, Florida, Bogota, Bulgaria, Cape Town, South Africa, all 4 people, I think, who've RSVP'd from there, Lithuania and India. Welcome, everyone. Let's jump into the presentation. Wait. Share the entire screen. This week, in preparation for the SQL Server 70-461 exam, we're going to be covering set operations, derived tables, and CTEs, or common table expressions. The presentation today is being done by myself. I'm Steve Stedman, and by Aaron Bouma, and we are on the research and development team at Emergency Reporting. Welcome for everyone joining remotely. One thing to keep in mind for any questions via the Google on-air broadcast, we'll try and address most of these questions at the end of the training, but and we will be using we will be using the Q&A tool inside of the Google on-air broadcast, and you can get to that by clicking the little 3x3 grid in the top right corner of your screen, and that then you'll have a choice for Q&A, and that'll slide out an area with questions. People locally in the room can just ask questions as needed. Some of them we may table for the end, some of them we'll try and answer as we go through it. Keep in mind that from when we say something here until when it shows up remotely, there's about a 40 to 50 second delay, so that if you're asking a question, it appears to us that it's 40 to 50 seconds delayed because we're getting that question as you're hearing us talk 40 to 50 seconds late. We're still learning how to properly use Google on-air broadcasts, so please be patient with us. This is our second time broadcasting live this way. And sessions will be available on my YouTube channel about an hour after the presentation ends, or you can click back to where this presentation or where the session is, and you'll be able to link to it from there. And that's available at stevestedman.com/YouTube. So when you ask a question, keep in mind it'll be about 40 to 50 seconds delayed. Things we're going to cover today will be set operations, derived tables, and common table expressions. Set operations, Aaron's going to cover that first, then we're going to cover derived tables. Derived tables, I'll cover that. It's just going to be enough information that we need as a foundation to get into common table expressions, and then next week we'll go into much more detail on derived tables as well. So I'm going to hand it over to Aaron at this point to cover set operations.
Right. Set operations. We're going to cover union and union all. Those are 2 types of set operations, along with intersect and accept, and the differences between those and how those are similar to the union and union all statements. All right, the 2 types of union statements, there's union and union all, and they're very similar to each other, except union all will return duplicates, whereas the union statement will return a distinct set of results. Things to note is when you do an order by, it will apply to all results in the statement, and you can have up to 256 queries that can be union together. All right, so now we're going to hop over to Management Studio. All right, so this is the set operations script, and at the top here we have some statements that will set up our training data. So we drop and create the database, drop and create inventory table, and insert it with some data. The data we're going to use this week is for kind of a sporting goods store inventory database, and it's just a single table that has item information such as category, the SKU, description, quantity on hand, unit cost, unit retail, and archived. So first we're going to look at some inventory. We're going to get all the items in the category sleeping bag and all the items in the category of food. We can see, two results here, two result sets. The first one is all the items in the category of sleeping bag, and the second is all the items in the category of food. So now we're going to use the union operator to combine those two result sets. We can see that this single result set has 3 items in the category of sleeping bag and 3 items in the category of food. So I know I went over the rules earlier, or they were on the slide, but we'll show them anyway. So what if we use different columns in the union statement? The first column is category, and the second column in the first query is item SKU, and the second column in the second query is quantity on hand. And we get an error saying that there's a conversion failure between varchar and int. So they have to be the same data type when you are unioning columns together. So what about a different number of columns than that? And we get an error message saying that we must have an equal number of expressions in their target list. So we have to have the same quantity of columns and the same data type for each column. So what about, how does the union handle nulls? We'll run these 2 statements here and see the category and unit cost for items with the category of sleeping bag and items with the category of food. And we can see that in the first result set, sleeping bag and unit costs are repeated 3 times. But for the food items, one of the results has a null unit cost. So first we'll try it with union. And we can see that the union statement actually sort of did a select distinct on that first query, and it collapsed the result set down to 1 row, and it returned a null. And now we'll run the union all. It's the same query, but we'll just add an all on there. So now it says union all. Union all displays all rows. It does not perform any distinct function on the result set. It also included the null.
How did it determine the distinct, which column did it give distinct on?
So the question was, how did the union statement up here determine which column to do the distinct on? It actually applies distinct to the entire result set. So if over here in this food query I was pulling from, say, unit quantity, and the data types matched up, and we just happened to have a quantity of 5.75, well, it would still show because the category is food, but it applies the distinct over the entire result set. So that's why the sleeping bag rows went away. Okay, so now we'll look at order by and how it applies to the individual queries and to the overall result set. So I'm going to run one query to show us all the items with category of food, show their unit cost, quantity on hand, ordering by quantity on hand. So that first query, let me scroll up here so you can see both. We can see that this query right here, when we're ordering on quantity on hand ascending, you would think that if I had it in this union statement, the top one result would show a quantity on hand of 1. But we can see that in the second one, when we did the union all, it returned the second row of the first query. And that happened because before it applies the order by, when you do the union all, it runs all the queries inside and then applies the order by to the entire result set. So as we learned last week in the top function training, if you have a select top one without an order by on it, you don't. It's a crapshoot. You don't know what how the table is naturally ordered and what results are going to come back. So that is why we see this quantity of 5 here. When if we pull the query out, we would see a different number. So that leads to the question: how can we get a top one out of a query that we are unioning to another query? And you do that with a derived table. You can see here that we return the item row for the food category with the quantity on hand of 1. So that leads us to the intersect and accept operators. And these are very similar to the union and union all, except they can only be used with 2 tables. Intersect is similar to an inner join, but on all fields. You kind of see in these Venn diagrams here, kind of show how it works. The accept operator will return all results from the first query that do not match the second query. It's not the opposite of the intersect, where it would return results from the first query and the second query that don't match each other. It will only return results from the first query that don't match the second one. So it's similar to a left join, where you're checking, or you have in your filter, your where clause, where the second table results are null. Here's some samples. So in this first query, I selected 2. The first result set is a select category and unit retail from inventory, where the category is in food intent. So it'll return all the items. And then in the second result set, it is an intersection of the unit retails for the items in the category of food, intersecting the unit retail for the items that are in the category of tent. So it will return the results where that column matches in both tables. Now we will run the equivalent accept query. And it returns results from the first query, which is the food items. You can see right here that do not match the items in the tent category. So we do not see that 99.95 unit retail anymore. We see the 7.99 value. So it accept is like a not in statement or a left join with null checks. And that leads us to derived tables. Steve.
Thanks, Aaron. All right, so let's jump into derived tables. Derived tables is one of those terms that I really didn't understand for a very long time, to be honest. I was using SQL Server for a long time and using subqueries, which is basically you put a query inside of parentheses and it gets treated as a table somewhere. Well, found out later that's really called derived tables. And if you're using other languages, like I think MySQL's query SQL language refers to it in their documentation more as derived tables than SQL Server generally does. So a derived table is simply a subquery. And there's a whole lot of stuff you can do with derived tables, but for today, we're just going to hit on the basics. We'll go into more detail next week. So with a derived table, you're taking an entire select statement, as shown here inside of the red box, and putting it inside of another query. And the result set of that is then treated as a table. So the term derived table, it's not a real table, but the output of the query is effectively a table. It's stored in SQL Server in memory as though a table would, kind of like a temp table in sort of a temporary storage location, not using the temp DB in the same way, but it's using that so that the output of that is completely isolated from the internal query and it can be used as a table. So in this example, we have the from clause, parentheses with the subquery, and then we give it an alias. So here I'm going to call it derived table. This is really useful when you have things like the ranking function or the rank function where you can't use that in the where clause. But if you put it in a derived table, it realizes that value into a table, and then in the where clause, you're able to use, in this example, like the rank unit cost that comes out of it. You also have the option of nested derived tables. And this can get pretty hairy over time. I've seen examples where you might have 10 or 12 or even 15 deep nested derived tables. The problem you run into with that is oftentimes these subquery pieces may get replicated here and there in different parts of the query. So I can remember opening up SQL Server report and copying the query out of it and seeing that it was like 4 pages long if you were to print it out on paper, and the same subquery was repeated many different times inside of there. So it can be very error prone, but it can allow you to do things that you wouldn't otherwise be able to do if they weren't pushed into a subquery or a derived table like that. Now, stepping back, what I've shown you so far is using derived tables in the from clause, where effectively you're replacing the table name that would normally go in what you're selecting from with a derived table. You can also use them in other places, like in the where clause. However, in this example, your derived table, because it's being used to compare a single value here of unit retail, you have to return only a single value from it, otherwise SQL Server throws an error. You have to use the distinct, and in this example I use distinct, and I'm calculating a rank over unit retail. I'm then determining the average rank, and I'm figuring out where unit retail is greater than the average rank. Now, the logic on that one may not make entire sense for why you would do it that way, but it was an example to show here's how you could put it in the where clause. And again, in that where clause, it's a single conditional. You're just checking to see if that item is greater than something. That something is the derived table that returns a single value, and that could be nested 2, 3, 4, 10, however many levels deep. Clean code isn't always a good idea to go that deep when you're nesting those. With common table expressions, a little bit later, I'll show you how to do that a little bit better than doing the deep nesting here. You can also use it in the column lists. So for instance here, I'm just saying select star from inventory. However, the second thing that's being selected there past the select star is a subquery or a derived table. So it's saying select distinct average unit rank, and this happens to be the same subquery I used in the previous one. So for every row, you're going to get all of the columns returned out of inventory plus another column that's being calculated for the average unit rank over that subquery there. The problem you run into with this, big red danger warning here, this will be run once for each row in the result set, and it may introduce some really, really serious performance issues. Now, if you're working on a table that has 7 or 8 rows, like the demo table that I'll be using here in a few minutes, yeah, no big deal. It's not going to add that much to it. But if you're selecting 10,000 rows or 1,000,000 rows or something ridiculously huge like that, this inner subquery, and in fact there's 2 of them, it's going to get run that many times. So if your result set returns 10,000 rows, that subquery is going to run 10,000 times, and the inner one is going to run 10,000 times. So you might get 20,000 runs of queries in a single select statement. Danger, danger, danger for performance there. All right, let's jump into the demo and take a look at the code behind all of these. I'm going to jump over to a different window here. We're using the same query training database that Aaron just used, but I'm just going to recreate it. Similar inventory table and similar products that are filled in that inventory table. I'll drop the database, recreate it, create an inventory table, fill it up, and then I'm going to use the query training database, and then we'll take a look. So if we wanted to look at how you can get the items with the lowest 5 unit retail prices, and from a couple weeks ago we looked at ranking functions and how to do this, well, you might think if I just run the first query here, select everything and then rank that over the window of ordering by unit retail, there's the whole thing. But if I want to filter that down to just the 5, you might think, well, just give me the 5 where the rank is less than or equal to 5. but that doesn't work because you can't run windowed functions in the select or order by clause. So then I think, okay, well, why don't we try having and see if that works? Well, we try this same thing with having, and you get a slightly different error message, but it pretty much says the same thing. You can't do it. Well, I don't like it when people tell me I can't do things. So here's how we can do it. We can take the basic select statement to select everything out of the table with a rank over the windowing clause like we were looking at. We can run that, and that's the handy thing about working with the subquery or the derived tables or subqueries this way, is you can just select a chunk of it and run that by highlighting it and hitting execute inside of SQL Server Management Studio. You don't have to select the whole thing. So you can now see that when we run this, we get our rank unit costs, and we're only looking for those that are less than or equal to 5, and over here that's going through 6. So by putting the parentheses around here and aliasing it, it's taking the result set that we're seeing on the screen right there, storing it off in some temporary location so it can be treated and used exactly like a table would be used in SQL Server. We now run it, and we're able to use that rank unit cost that came out of the subquery in our where clause and filter it down to just the top 5 rather than anything beyond that. So now if we want to take a look at the 5 cheapest products, but show me those that are priced above the average of the 5 cheapest. Okay, kind of weird, but let me rephrase this to make sure everyone understands it. Out of all the products in the store, I want to look at the 5 cheapest, and of those 5 cheapest, show me those that are priced above the average cost of those 5 cheapest. Now, that's a really tough query to do if you don't have subqueries or derived tables. So we're going to start with that same query we looked at a minute ago, where we're going to rank it ordering by the unit retail, which is the retail price. When we run it, we can see here they all are, and there's a tie in here actually, so we can see that 2 of them are at this same retail price of $19.99 here. We're then going to, in the next level out, average all of the unit retail prices, because we couldn't put that average inside of here because it doesn't work quite right that way. So when we run that, make sure I got it right. So we run the inner one there, and at this point we're going to filter it out and throw out everything other than the 5th one, which is very similar to what we did in the previous query. So there we get all the products, the 5 cheapest ones ordered by cheapest to least or more expensive, and then it shows the average cheapest product here is $17.58. So next what we need to do is we need to filter on that, but we can't filter on that value because it's being calculated on the fly here. What we're going to do, is put it inside of another subquery and add the where clause down below and say where the second derived table, which is the outer derived table there, is value of unit retail is greater than the average cheapest item, so the average of those 5 cheapest. And there you go. We can see that the 3 values that get returned are the 3 that are above $17.58 at $19.99, $19.99, and $24.99. All right, so now that covers the basics of derived tables in the from clause. Let's take a look at using it in the where clause. So we'll go back to a simple query here that just shows us what we've got in the table and ranks everything in the unit retail column, or the price. Oops, I highlight the right thing and run it. There we go. We can see, again, as we looked at, they're ranked through 1 through 6. But if we want to then filter or include a calculation in the where clause, we can build it out this way. And I always, when I start looking at how does a subquery or a derived table work, I always start with the innermost one to understand it the most. Select rank over order by as unit rank from inventory. Same one we looked at a minute ago. When we run that, you see we get ranks 1 through 6. We then go 1 level out, and we're going to say select distinct average unit retail over. So when we run this one, what did I do? Oh, not enough parentheses. There we go. We run, select rank over from DBO inventory. There we go. I didn't have the right parentheses lined up there. I think if I'd done just this. No.
You need to add two.
Yeah, so I include that, and what I get is that the average rank over 1 to 5, or over 1 to 6, is 3. So then that's being used in the where clause, and because of how this works, it gets run once, and then evaluated against every rank unit cost in the entire list at that point. Now we can take a look at how to use it in the select columns list, and this is the one that I said can be really, really inefficient if there's a lot of rows there. So same thing, we'll start with the innermost one. We can see we get the unit rank of 1 through 6. We then select the average out of it. There we go, we get 3. And then we can say select star over or from inventory with that subquery or drive table inside of the select statement. Now keep in mind that when you're using it in the select statement like this, it has to return only a single value. You can't have it return multiple rows or multiple columns. Otherwise, SQL Server doesn't know how to match it all up to be able to put it in the select statement there. So when we run that, you can see we get all the normal values down here, but it shows us that average derived table column over here. Now you might look at it and say, well, why couldn't you just use an average with a windowing function and do that in that same place? Certainly you could, but this is showing how you could use derived tables to come up with what you need in the list of columns in the select statement. So that's it on the basic overview for derived tables. Next week, we'll jump into a lot more detail on that, but I just wanted to kind of hit the overall foundation there so that we can jump into this next section. Common table expressions, or CTEs. This is one of my favorite topics in SQL Server, and it's one of those things as we jump into it. Well, I wrote a book on it, and it was published in May of 2013, and it covers probably everything you ever wanted to know, plus more that you never wanted to know about common table expressions. And it was a limited time publication. You might be able to get it on Amazon, you might not. But a lot of the content that's available here is available on my website, and a lot of the content in the book you're going to be able to download at the end of the session as well. Today we're going to cover topics out of chapters 1, 2, 3, 4, 6, 7, and 9 out of the book. So as we're flipping through here, you might see a title section that refers to chapter 2 or chapter 3. That's just the chapter in the book that's being used there. Thing we're going to cover is introduction to memory tables and CTEs. Start with a simple CTE, and I guarantee when we go through the simple CTE, everyone's going to look at that as, wow, this is kind of boring. But that's okay. It's just a foundation so we can build to get to the rest of it. How to use a CTE instead of a derived table. So when you've got those big, nasty derived table queries that are 4, 5, 6 pages long, you can learn how to clean them up and make them cleaner code and more readable. We'll take a look at how to use multiple CTEs in a query. Take a look at data paging, which we've learned top in the past, but we'll take a look at some other ways to be able to page data without just using the top function. And then how to use them, CTEs in stored procedures, functions, and views. And then we'll take a look at what's my favorite part of the whole thing is how to do recursive common table expressions. So quick show of hands in the room, how many people have used CTEs before or know what a common table expression is? Okay, a couple, that's all right. So let's start out here with what is a CTE? Well, in SQL Server, there's this concept of memory tables, so sort of this virtualized or virtual table that gets built in memory that, like what we just talked about a minute ago with derived tables or a subquery, where you're running the query, that result set is being stored somewhere so it can be used. For instance, with the subquery that I've shown here. That's one way that there's this sort of in-memory table that's used. Views are another way to do that, where a view sort of stores this query and substitutes it in what you're running in order to be able to clean up your code a little bit. In this example, there's a view that just selects those columns, and then we select from that view. Views are a really good way to clean up your code. However, they're hard to maintain over time when things change in the database. They oftentimes get overlooked, and they just sort of tend to rot over time. So I try and stay away from views when I can, unless there's a really, really good reason to do it. And then you've also got the concept of these temporary named result sets, where you have a temp table or a table variable. And this is where it's not a table that's stored in the normal database area, but it's stored in tempdb. And you can create this table and shove information into it, and it stores information there temporarily for you. You can come back and use it later in your query. However, the last one we've got is another way of doing these kind of memory tables is to use common table expressions. Yeah.
Do they stay? How long do they stay in memory? Do they stay in memory during the query, or can you access them after the query?
Which ones?
The views or the memory tables.
Okay, so the question was, how long do they stay in memory? And do they stay in memory just for the query or for longer than that? With virtual tables like a derived table or subquery, that's purely the life of that single select statement. Views are kept around when you create a view indefinitely on SQL Server until somebody drops them. Temporary named result sets, as long as you're cleaning up your code after you, and you're not doing global ones, you'll have temp tables, and temp variables will go away at the end of that query chunk of code. Not a single statement, but a single batch of code. And then common table expressions are only available for the life of that single query, similar to how derived tables are. So what is a CTE, or a common table expression? And it's not one of those things we can say, well, it's just like this. It's just like this thing that you all know in your everyday life, because there's nothing quite like it. So it's a type of a virtual table. It's similar to the ease of a temporary table, meaning the way that you use a temporary table. It's just you're accessing it, using it kind of like that. And I'm using sort of and kind of a lot here because we'll get into an example of how to use it. But it's sort of like a derived table, like we talked about a minute ago. And it's kind of like a temporary named result set. So if you could run a result, save that result somewhere, and then use it, that's kind of what a CTE is like. And it acts like a temporary view or a runtime view. So availability of CTEs. CTEs, they were introduced in SQL Server 2005. And I wished I had learned about these 10 years ago. I've only known about CTEs for about 5 years now, but I think, well, there are a lot of really cool things introduced in SQL Server 2005, but it was one of my favorite overall, I think. It's supported in all versions of SQL Server since 2005 and all variations of SQL Server, including SQL Azure. Now, some of the really cool features that are available in SQL Server are only available if you're using the Enterprise Edition, or only available in a certain scenario. But this is just part of the core of SQL Server, and it's available everywhere. This is not on wireless. No,
Okay.
I don't. Am I disconnected, or is that disconnected?
That's this computer.
Yeah, I seem to be broadcasting fine.
Okay. Go on.
All right. So available in all versions of SQL Server since 2005, including SQL Azure. Okay, so why use this? Why use common table expressions? It's another tool in your tool belt, basically. Why would anybody want to use this when I know how to use a derived table or a subquery? Well, it's a great way to simplify your query. Like I mentioned earlier, you can have a big query that might be 4 or 5 pages long, and you look at it and you think, where the heck do I start to understand what's going on here? Well, you can break your query up into more logical pieces using a common table expression. You can use it for recursion. Now, in computer science, recursion is considered is what when a function calls itself, or a function calls back to itself to do recursive type calculations. In SQL Server, it's when a query calls itself. I think, well, how do I do that? I've never seen how a query can actually reference itself inside of it. Well, that's what we can do with common table expressions. And it's a way to make derived tables queries more readable, and it's an alternative to temp tables or table variables. Now, keep in mind also, it's just another tool in your tool belt. So don't think that it's a reason to replace everything you ever do with derived tables, or it's a reason to replace everything you've ever done with temp tables. There's great reasons to use temp tables. There's great reasons to use derived table or derived table queries or subqueries, but it's just another tool to use when it's appropriate. So the way it works is the syntax starts with the word with instead of select. Pretty much everything you run in SQL Server that's going to return some type of data, you start out with select, but not in this case. It can be confusing if you're assuming that any query that select data would start with select. And in regard to the question earlier about how long are things kept around, the scope of the CTE is confined to a single query. Meaning when you build out a CTE and you run that select statement and you have that semicolon or the end of that select statement, it's gone. It's done at that point. You can't use it again in the next select statement. So that's an example of if you want to pull data back that was being used by multiple select statements, you might want to put it into a temp table or a table variable instead. And CTEs are just a little weird until you master the syntax, and maybe that's why I like it. So the basic syntax starts out using the with statement, and most of the time when you're writing T-SQL, the semicolon on the end of your statement is an optional thing. However, if you have multiple queries in a batch inside of T-SQL with CTEs, if the previous statement is not terminated with a semicolon, your CTE or your with statement will fail at this point. So one habit I've got into is generally I'll put a semicolon at the beginning of the with statement, just in case it's being copied and pasted to somewhere where somebody forgot to put the semicolon at the end of the line. Our clean code standards generally dictate that we always want to use semicolons to signal the intent that the query is complete. However, it gets missed occasionally. So here it's with, and we give it a name, and then you can define some columns here, but they're completely optional. There's certain cases where you have to do it, but most of the time you don't need it. And then you use the word as, and just like in a subquery, you're going to put sort of a subquery type query inside of parentheses. And then we're going to select columns out of the same expression name that the CTE was given up top here. So let's jump in and actually look at a code example here, because that's a much quicker way to really understand it. So here I'm going to use the same query training database. I'm going to drop it, and then I'm going to create a couple new tables. The first one is called royalty, and this includes British royalty, and it has a name, an ID, and a mother and a father to indicate sort of a family tree type structure here. And then I'm going to create a departments table, again, not related to royalty, but just good for the example here, where we just have a department ID and a parent, so it's a hierarchy as well. I'm going to create a stored procedure which fills in a bunch of data into the departments table. And then I'm going to create another stored procedure called fill more departments, which is going to put even more departments in it later. And then as I run through the query, we're going to use the data that gets put there a little bit later. And we're going to change some, we may change some of the data along the way, so that's why the reload departments has been put into a stored procedure. So we'll execute this, we'll reload the departments, it just fills in, I think, the first 16 departments, and the royalty table has been built out completely at this point. We can then select star from departments and see what we've got there. We've got IDs 1 through 17, and then it shows what the parent departments are. So all of these here in this category are under the department campaign and et cetera there. Then we're going to take a look at royalty, and we've got George, the King of England, Mary, Princess of Tech, I guess, George the 6th of Windsor, and so on all the way down here. And as we scroll all the way through here, it's just a bunch of the British royal family, and it'd be really nice if you could see it in some kind of a better structure than this. But it's simply all the royals back a few generations with who the mother and father are at each level. So that's the data we're going to work with. So let's start out with a simple CTE. Here, we're going to select 3 columns out of departments. And again, like running a subquery, I'm just going to run the inner one and test it. And you can see there we go. We get ID, department, and parent from departments. We're going to wrap it with a common table expression using the with department CTE. We declare the columns we're going to get back. Now, this declaration just covers the names of the columns. It doesn't give you any data types or anything like that. We use the as statement, and then we're going to select everything out of department CTE. So at this point, we've just done what's very similar to what could have been done with a derived table query. Not real exciting yet, but hopefully everyone follows the syntax there so we can get to the more exciting stuff. All right, so then earlier I mentioned you got to have the semicolon at the end of your statement. And I usually put a semicolon in front of the with statement. So let's look at what happens if you don't have the semicolon there, because you'll probably end up doing this sometime or another. So here, select star from departments, no semicolon, with no semicolon in front of it. When we try and run it this way, we get this great error about if this is intended to be a common table expression, you need to explicitly terminate the previous statement with a semicolon. So when you see that either you put a semicolon in right here, or you can put one in front of your with statement. Here's probably the best way to do it, but with statement's a good spot for safety. All right, so let's jump back to the PowerPoint here. That's the simple CTE, is simply like a subquery, but you're referencing it as a named, almost like a named subquery in that point. So keep in mind, if the CTE is not the first statement in the batch, it must be preceded with a semicolon. All right, so let's look at how we can take CTEs to replace a derived table. Derived tables, for anyone who's used them much, they just get ugly over time. And the derived table is a great way to simplify the query and allow for cleaner code. It's a way to break it up so it makes much more sense in what you're viewing when you're looking at a query. When you write that 4-page long query with 17 different derived tables and 6 different chunks of copied code, it probably makes a lot of sense at the time you write it, but if you come back a year or two later and look at it, you're not going to be able to make heads or tails out of it. CTEs are a great way to break that up so it makes more sense. Keep in mind, though, that using a CTE does not change the performance at all versus a derived table. So if you've got a derived table subquery that's being run twice somewhere in your existing query, there's so much work to make that happen twice. If you're referencing that as a CTE twice, it's still just the exact same amount of work. So there's nothing being saved there. The results aren't being saved. When you use a CTE name, it runs it a second time, or a third time, or a fourth time, depending on how many times it's referenced. And you get more value out of it the bigger the query is that you're breaking up. And you eliminate accidents that are caused by duplicate code in your derived table queries. I don't know how many times I've looked at a derived table query that was really nested deep, and I realized there's a chunk of code up at the top that needs to be changed. But then you realize it's got to be changed at 6 more times all the way through. You run the query and it doesn't work. You look back and you realize, oh, it was supposed to be run at 7 times or fixed 7 times, not 6 times. And those are just a pain to maintain. So let's take a look at how we can do this to replace this example. So highlighted in red or in bold if you're colorblind is a derived table subquery that's replicated twice here. And you can imagine that could be used 4, 5, 10 times, whatever, in a bigger query. But it's error prone, and the bigger the query gets, the more error prone it gets as you go through this. But we have 2 exactly the same queries there highlighted in red. You could put it in a view. That'd be one way to do it, but views have other issues you've got to deal with. You could have a function that returns that. You could go put it in a temp table, but an easier way to do it is with a CTE. So the way we do that is we find the first occurrence of the derived table query, and we create a name for it. Then we copy the derived table definition out into the CTE, including the parentheses, and leave the new name as the placeholder. We then paste it in, paste the query copied earlier into the select statement. We then at the top of the query, we add the CTE declaration, and we find all the occurrences, and we clean up the formatting and test the query. So the example of what we could come out with after doing all that would be this. We grabbed the red part here out of the original query. We added the with syntax up here. We gave it a name, and in this case, I'm calling it Department CTE. We declared the columns here, which in this case are optional, but for clean code and being explicit, I'm going to call them out. And then Department CTE got referenced twice down here. And although we've got about the same amount of code on this slide as we did previously, we don't have the duplicate code with the same kind of duplication problems that we would have before. This is a great way to just clean up the code. And if you were working with a much larger query that's on the inside of the CTE or your derived table, you would have saved a lot more space there. So let's take a look at a demo of actually doing that. So here's that derived tables query that we looked at, where we've got this select statement and this select statement repeated twice in the same query. When we run it, you're going to see that we're getting all of the parent departments and all of the sub-departments returned here. And it's just basically what you'd call a self-join back to the subquery. But technically, it's not really a self-join because it's 2 different things, 2 different queries as it's being parsed through SQL Server. So let's take a look at how we would break that up. So what we could do is take this whole query and copy it. We then take this inner part out here, paste it up here. We then say with Department CTE, and I'm going to skip the columns at this point because just to simplify it and show an example. as that broken out with parentheses. I'm going to copy the CTE name, put it in here where we copied from, go replace the other subquery with that department CTE, clean up the formatting a little bit, and depending on your standards, you may do this in several different ways. Clean up the formatting kind of the way I like it here. And then we highlight the whole thing and run it. It's always great when you do typing in a demo and it actually works correctly. So we get the very same results that we saw a moment ago. But in this case, we've eliminated the duplicate code. So if we realized that we had to go in and do some work and say, well, instead I wanted to return these in a different order or from a different table, we only have one place then to go fix that code rather than two places in that specific query. And here's the prepared earlier version of the same thing. You can see we get the same result I just created. However, this one, let's see here. Yeah, so that's pretty much what we came up with in the fixing it up there. So let's jump back to the PowerPoint for a moment. And let's take a look at how we use, or just a summary here, I guess, on the derived tables. So most derived tables can be easily converted into a CTE. Some of them that are really big and nasty may take a little bit more work to figure out where you copy and paste, but it's mostly a copy and paste kind of a thing, not an actual code issue you've got to deal with there. Copy and paste errors can be reduced with that CTE, and using the CTE does not improve performance. So if we jump back to the code here, even though we've only declared this select statement here once, it's being referenced twice, and each time it's referenced, it gets executed another time. So there's no performance increase over doing it that way, other than it's just cleaner code and maintenance will be a lot easier with it. All right, on to multiple CTEs in a query. All you have to do to include multiple CTEs is separate them. So here's an example. We start with a semicolon with our first CTE, and then inside of parentheses, we have our normal query. You can have a second one with a second different query here. It would never make sense to put the exact same query in because you just use the first one in that case. And then we can select something from the first CTE and join to the second CTE on some column they might have in common there. How many of these can you have this way? You can have more than you would ever want to use. I don't remember the exact depth, but I did some testing when I wrote the book, and I used an Excel spreadsheet to create just stupid amounts of depth there. Between 2005 and 2008, the number went up, but I've done done queries like this where it's had over 30,000 CTEs in the same query. If you're doing that many in the same query, you probably want to go back and read the clean code book and start over again. Or maybe redesign your data because something's gone really wrong. So steps to add the second CTE. Here's an example where I threw in a simple query here that just selects John, Mary, and Bill and unions them into a result set. So we're getting 3 rows returned by that, and we're going to call it first names. I then add a comma. I give it the name of the next CTE, and the name of the column is being returned called name. And here I'm going to select Gibb, Smith, and Jones, union all of those. And then I'm going to do a cross join. And if you're not familiar with the cross join, what it does is it takes all of the data from the first table and joins it with all of the data from the second table in every possible combination that there can between all of those. So the result set from this would be John Smith, John Gibb, John Jones, Mary Smith, Gibb, Jones, Bill Smith, Gibb, and Jones, all the way through. So you're able, it's one that's pretty handy as a way to be able to build out lots of test data real quick. Some companies out there make apps that you can run that will fill up your tables with a bunch of test data. I like to use this kind of an example with maybe a few more names if I want to fill out a table to see how it's going to perform if there's thousands of rows in it, and then you can just use the go statement and fill it out with lots and lots of data this way. Okay, so we'll take a look at multiple CTEs, and then we'll come back and take a look at how these can be nested. So here we're looking at the subquery version of it without CTEs, where we have a select statement that shows all of those with department ID of 4. And then here we're selecting everything independent of what the department ID is out of the departments table. And when we run the non-CTE version of it, you can see that department ID of 4 is fitness, and what we get back is all of the subcategories of fitness as running, swimming, and yoga. The way we would do that as a common table expression is we break out the first one here, call it department CTE top, meaning the top level. And then the department CTE levels is all of them below that. And then we use the exact same join statement, but it's referencing two different CTE names here. And you can see when we run this, we get the exact same result set, 0 performance change in any way whatsoever. However, when we look at the code, it's a little bit more cleaner as to what we're doing here. And normal in code, I would give it probably a little bit longer name of the CTE or a little bit more meaningful name of the CTE here. But for the purpose of the demo, I wanted to keep it short. So let's take a look at something similar to what we saw earlier. We'll take a look at using the union statement to bring back 3 names, John, Mary, and Bill. And you can see we get a result set with 3 rows in it. We then, I'm going to build a CTE that just puts John, Mary, and Bill inside of it and then selects the first name, f.name, where f names is f, and call it first name. We're going to run that, and we get the same result. Not very exciting yet, but here's where it starts to get more exciting. With f names, and that's the exact same name we looked at before for first names, and l names for last names. And we'll just run this one so you can see what the inner part looks like. We got Gibb, Jones, and Smith. We then select first name and last name cross-joining it. And you can see here, we get 9 rows. Or 3 of one times 3 of another is 9 different rows in the entire result set, generated it out that way. Now, if we want to do something similar and add a middle initial, A, B, and C, as another CTE, we then cross-join middle initials, we run the query, and we get 27 rows. John A. Gibb, and down here there'll be a John B. Gibb and a John C. Gibb, for instance, all the way through that way. Now, you can see if you copied out this A through C here and maybe built it out through A through Z, you could really build out a result set real quick this way with your common table expression. Another way you can do this with newer versions of SQL Server is to use what's called a row constructor. Instead of using the union, we can select from the values of all 3 of those as f of x, or as fx like that. I forgot one letter in the select statement. We get the same thing, and it's just a little bit different way to build out the same query. Not directly tied to CTEs, but it's just kind of a cool way to build out the same type of result set that we just saw there. Let's see, what else have we got here? Select first name, last name, and middle initial using the row constructor. Same thing. I'm going to skip over that with keeping track of time here and jump into nested CTEs. How many of you have seen these Russian nesting dolls? They're known as matroshkis at one time or another. Now, if you've got one of these and you look at the big doll and you try and fit it inside of the little doll, that's not going to work. It just doesn't work that way. Physically, you can't do it. But you could take the tiniest doll up there and put it inside of any of the larger dolls, and it would work just fine. Or you could put the second tiniest one and put it inside of any of the other ones, because of the way they all snap together. Nested CTEs kind of work the same way in that you can only reference itself or reference ones that are declared earlier in the query. So in this sense of the nesting dolls, it's kind of like referencing the smaller one or the one that's earlier in the set. We'll take a look at an example here. So with CTE 0, I'm just going to select 1 as a number. Not a very exciting query. But then with the second CTE, I'm going to reference the first CTE inside of the query and say with CTE 1, I'm referencing CTE 0 and adding 1 to it. Then I have CTE 2, which references CTE 1 and adds 1 to it. And I select star from CTE 2. Anybody know what our result's going to return when we run this? Three. All right, basic math, we got there. So let's take a look at that. Here we have, if we just select 1 as num, we run that, all we get back is just 1. We're going to have this CTE that's been referenced by that one, that's been referenced by this one, and then we're going to select star from it, and we get the result of 3 back. Okay, there's a lot easier ways to add 1 plus 1 plus 1, but it kind of shows you how one CTE can be used to reference the previous one to reference the previous one. But where you run into the problem is, if you wanted from inside of CTE 0, you cannot reference either of these other two because they haven't really been instantiated or created as SQL Server is going through the parsing of that statement.
Well, so in that case, can CTE 0 reference CTE 0?
So the question in that case was, can CTE 0 reference itself as CTE 0?
In this one, technically it can, and we'll come back to that in just a minute. That's a great question. I love those that lead into a further section. So yes, but it's not as obvious as just the way we've done it here.
I have a quick question. So if you try to access the CTE while it's executing, what if it's not finished yet, or is it possible?
No, it's really, it works a lot like a subquery, because when we say this here with CTEs, the question was, what if it's not done executing, right? Yeah. When we're referencing it. Well, you don't get that option. SQL Server takes care of all of that for you. So when you say select 1 as number with CTE 0, it's not actually usable down here until this is complete. So it stalls or stops waiting at that point until that processing is complete before it can be used later. So just like a subquery or a derived table, you never have to have logic that says, is it done yet? You just know it's done by the time the query is using it. All right, so now we're going to jump into an example here of data paging. The question about can a CTE reference itself, we'll get to that in a little bit, but this one here is building on how can we use CTEs without referencing itself. So data paging. So this is one that a lot of the times people use the top statement. If you're doing paging, like think of Google search results. You search on common table expressions and you get some of my website pages, hopefully, and then a million other results. But Google only shows you the top 100 results or the top 25, depending on what your settings are. But one way you could write code to do that if you're writing that web page is say, give me the top 100, and then display that on the first page. But then when someone clicks next to go to the second page, you say, give me the top 200, but let's just scan over the first 100. Not the most efficient way to do it, but I've seen it implemented that way in my career probably 10 different times now. Data paging has generally, when you're taking it from a database and bringing it into a web page, has always been an extreme pain for web programmers. Never fun until CTEs. And we'll show you how easy this can be and not be a challenge. SQL Server 2012 and newer has the offset and fetch keywords, which are an easier way to do the data paging than CTEs. But we'll show the CTE way of doing it, and then we'll show, if you're using a newer version of SQL Server, another way that you can do it as well. So think about it. Here's an example. I think I was selecting from sys columns table. And here we have row number 1 through 10 showing up on the screen. Then the second page in that data set might be rows 11 through 20. And the third row, or the third page might be 21 through 30, and so on. Now, the way you could do that is we take this inner blue select statement here, which is what would give me the entire set selecting from sys.columns, which is just, if you don't know what that is, in SQL Server, it's basically a view that gives you a list of what all the columns are in your database and what table they're associated with. So I could put that whole thing inside of a CTE, call it tables and columns, select from that, and say, here, I'm generating the row number. Because of the way that functions work in SQL Server, the row number can't be referenced in the where clause in the blue code, but in the outside, just similar to what you could do with a derived table, though, you can put it between, and here's some math that if we had variables for page number and page size, it would automatically calculate the row number to give us the right page data. The way you could do this with SQL Server 2012 and beyond is a little bit simpler, but it's not available in 2008 or R2 or 2005. Here you can use the offset and fetch next, where here you're saying offset a certain range. So you can say offset 5 rows, fetch the next 5 rows only. And it's just an alternate way of doing it. Let's take a look at a demo of actually using that code. So here we're going to be using that sys.columns, and I'll show you what it looks like. Whoops. Show you what it looks like to look at the whole thing. It's just pages and pages and pages of every column available in the SQL Server at this point. Then I'm going to wrap that. Oh, I also included the row number ordered by the object ID. I'm going to wrap that in a CTE called Tables and Columns. Then I'm going to select from Tables and Columns where the row number is between and doing the math to get the right rows based off of page number of 2 and a page size of 10. So if we highlight this whole thing and run it, you can see we get rows 11 through 20 at this point, and only rows 11 through 20. And that's far more efficient than saying, give me the top 20 and then just skip over the first 10. Now, the other thing we could do looking at this is we could put that into a stored procedure. So I'm going to create a procedure called Tables and Columns Pager. It's going to take 2 parameters, one for page number and one for page size. Turn on no count so we don't get row numbers being spit out or number of rows affected being spit out. We then put the same query in there. And then when we execute it, let me first just create it here. And then at runtime to execute it, we just say, give me tables and column pagers for page 1, 2, and 3 with a page size of 10. And if we scroll this up, we can see the first one covers rows 1 through 10. Second one returns rows 11 through 20, and the next one returns rows 21 through 30. So much, I don't know, in my opinion, much cleaner way than almost any other way I've seen of doing this to be able to do paging of data. We can also look at how it compares to the SQL Server 2012 way of doing it and newer. So this is 2012 and 2014, where it's using the offset and the fetch next. And what we're going to do is we'll highlight the whole thing here. This was set up for performance. We're not going to go to the performance. The performance is very similar with these. And the performance really comes down to it depends on your data set, your database, how things are configured. In some cases, the offset and fetch way may be a faster way to get at your data by a little bit. In other cases, the CTE version might be just a little bit faster. So just think of it as an option there on newer versions of SQL Server. 2 different ways to try something for paging or for actually doing any type of, for the paging work here. So we run this, you can see we get 2 result sets back. They have the same stuff in them. One of them using the CTE version and one of them using the offset and fetch. Now, if you're working with SQL Server 2012 and newer, and you know your code's only ever going to run on 2012 and newer, I would say, in this case, go with the offset and fetch. But if you have to write code that's portable to other versions of SQL Server prior to 2012, the CTE version is much more reliable in that case. Next, on to CTEs and stored procedures, functions, and views. Now, we saw an example there of putting it in a stored procedure, but let's take a look. Actually, I've just got direct demo set up for that. So I'm going to create a procedure called show departments. And in here, I'm just going to put a simple CTE inside of it, and then I'm going to execute it. And that's pretty similar to what we saw a moment ago when we looked at the previous stored procedure for the paging. But you can see just calling the stored procedure returns the result set that we can see here. CTEs work great inside of stored procedures. Just like a select statement, there's no reason you shouldn't use it inside of a stored procedure. Functions, very similar. Here I'm creating a table value function, and then I'm going to select from that table valued function. And you can see we get a similar result set back. So by putting it inside of a function and selecting from that function, similar results. And again, CTEs work great inside of functions. And how about if we put multiple CTEs inside of a function? Here, we're going to say, here's a department CTE. We're going to insert into a variable called results, or a table variable called results that's being returned. And then we're going to do a second CTE that inserts more into that table variable called results. And the results of both of these will effectively be almost like you're unioning them, or a union all, into the same table. So let's just create it. And if you're wondering why up here I've got the drop function in comments, when you're testing code and playing with it, you want to drop the function or else you can't create it again. You can always use alter, however, but it just kind of keeps it clean. So you can see when we do that, what we got, we'll jump back to look at the code here. What we've got in the result set is all of those where the parent ID is 1, which is these here, and then all of the items where the parent ID is 3, which are these here. Very similar to what you could do with union all or union, just a different way to do it. All right, so here's one where we've got a non-table valued function or a scalar function that's only going to return an integer. It can't return a table or a result set. We're going to declare the result as an integer. We're going to declare our CTE. We're going to select a count from that CTE into that variable and then return the variable. That works great also. But just keep in mind that if you're doing a scalar function that returns a single value, you can't return a whole result set there. It has to be a single item that's being returned. And then in views, you can also put CTEs inside of views, just like you would do with a select statement. We'll create the view, and the earlier question was, how long are these things kept around? Well, that view, now that I've created it, is kept around until it actually gets dropped or deleted from the database. And then I'm going to select from that view. There you go, similar result set coming back. So, stored procedures, functions, both scalar and table valued functions and views, CTEs work great inside of all of those. Now on to the really fun stuff, recursive CTEs. And now the reason I say this is really fun is the stuff you can do with recursive CTEs, you can't do very easily any other way with SQL Server. Yeah, you could do a function that ends up somehow calling itself, and it's really messy and really ugly, but CTEs give you this sort of elegant way of doing recursion. Question?
Do the CTEs have to be processed linearly, like parallel versus like actual when they're being processed?
Oh, great question. So do the CTEs have to be processed in parallel or linearly when they're being run, or sequentially?
Yeah.
That will depend on one of the things that you can set up in SQL Server is your max degree of parallelism, which tells you, given a query and how complex it is, how many parallel processes can take it on. So if your CTE is simple, it might get run as a single thread, single process in SQL Server. If it's really complex, or if the SQL Server query analyzer determines that it's a high cost, it may split those out and run them in parallel, depending on what needs to be done there. But it can't run one that depends on another in parallel to that, of course.
Right.
So yes, you can get some better performance out of it that way. So recursive CTEs. It's considered recursive when, back to the question we had earlier, can a CTE reference itself? It's considered recursive when the CTE references itself. Recursion stops when the query produces no more results, or there's just nothing returned at that level of recursion, or when max recursion is hit. Max recursion is a parameter that's set up in SQL Server. The default is 100, but you can extend it out to as deep as 32,768. I wouldn't recommend doing that unless you've got a really good reason for doing that. And actually, now that I think about it, on the newer versions of SQL Server, I think you can go beyond 32768. Great way to use this is for a hierarchical listing of categories, recursive calculations, and much, much more. So recursion, what is recursion? Well, if you were to sum the numbers from 1 to 10 without recursion, it would effectively be saying 10 plus 9 plus 8 plus 7, 6, 5, 4, 3, 2, 1, all the way out equals 55 in this case. That's sort of the non-recursive way of doing it. But with recursion, it's kind of like saying, give me the sum of the numbers. It's just take 10 and add it to the sum of the numbers 1 through 9. And then when the sum of numbers 1 through 9 is processed, and then continuing out all the way as though you're doing each of these as a different function call to be able to work through that code. You can do the same thing with common table expressions. In CTEs, where it all starts with recursion is what's called the anchor query. This is where recursion starts. And you can have one or more anchor queries. And I'll show examples of that too. Now you might think, well, why would I have two different anchor queries on recursion? Well, it'd be just like in code, if you had two different recursive functions that were being called in different areas, the anchor query is two different ways of starting that recursion. And then you have the recursive part of the query, and this is the part that gets repeated for each level as it's walking through a hierarchy or walking through the levels of data here. And you can have one or more of these as well. And then max recursion, like I said a minute ago, the default is 100, And this is really handy to keep your query from going out of control. I've done some recursive queries that were designed to see how mean, how evil they could be to SQL Server, and I've effectively been able to chew up all of the available memory it's on a test machine with only 16 gigs of RAM, but I was able to use it all up in a single query by getting a bit wild with recursion. So max recursion, you can set it to 0. That implies there is no maximum. So remember now, if you're using numbers, the maximum you can do is 32768 for your depth, but 0 will let you go beyond that, meaning just keep going until your query finishes or until SQL Server runs out of memory. Danger, danger, danger.
Or you ran out of customer.
Yeah. So the way it works, start out, you declare the CTE in columns. Very similar to what we've done before, but in this case, I'm adding a different one in here called level. I should have clean code made that spelled that out effectively as level, but I think level was a keyword in SQL Server, so the syntax highlighted showed up weird, which is why I abbreviated it. Then I'm going to start out with a real basic query. I'm just going to say, give me department ID, parent, and 0 as level from the departments table where the parent is null. Okay, so give me all the top level departments at this point. Thanks, Aaron, for the training on union and union all earlier. We're going to use the union all in here to connect that anchor query, which is in blue, to the recursive query. Recursive query is highlighted in red, where it's pretty similar. We're going to say select this, that, and the other thing from departments, but we're going to inner join to department CTE, which is declared up here. So inner join back to itself on the department ID equals D, which is departments.parent. So it's going to take your top level and then find all the next level in the hierarchy. And then this level variable, which is how deep into the recursion have we gone, I'm just going to take the previous one and add 1 to it. And then I'm just going to say select star from that entire query. Okay, it's way more fun when we jump into the code. So here we're going to look at departments again. There we go. We've got the same department table we've been looking at all day long here with the same type of stuff. With a total of 17 rows and a number of things scattered out amongst the 4 top level departments which have no parent. Then we're going to just say, give me the top 4. Give me the top level ones that don't have a parent. There's the 4 of them. So those are your main categories as you look at the store. Now, how would we do this without a CTE? Well, we could use a self-join where we select departments and join it back to itself. And show top level and child level. Okay, so there's all the top levels, there's all the child levels. Yeah, no CTE used there, but we don't have a level. So if we want to use a level that shows us how deep in the hierarchy we were, we can use this case statement in here that says, if the parent's null, then we're at level 0, otherwise we're at level 1. So we run that, and we can get the level listed over here. Great if we got 2 levels, but if you want to go 3 levels or 4 levels or 5 levels, prior to using CTEs, I saw some really, really darn ugly queries where people did this out for 4, 5, 6, 7, 8 levels, and you just end up with horrible code to maintain. But here's how we would do that with a CTE in a much cleaner way. Here I'm going to select the top level and just say we're at level 1. Actually, let me correct something here. That's actually level 0. So the top level is level 0 just to match the samples we had. And then I'm going to throw that inside of a CTE. Not very exciting because we've just got the top 4 top level categories here, but that's the foundation for where we're going next. Next, this piece here is the recursive CTE part of it. And because it references the CTE, we can't just highlight this and run it outside of the CTE. So we copy that chunk using union all, we paste it in here, and we say select this query, and then for every row returned from this, inner join it into this result set. We run that, and we can see we get back to similar to what we saw a moment ago, where we can see the top level and then all the second level stuff. Okay, great. Still not that exciting. You could have done all that with a self-join. But what happens when you've got more departments? So I've created this stored proc called fill more departments that's going to put in, I think, a 3rd, 4th, and 5th level into the hierarchy. When we run that and we go back and look at the non-CTE version of it right here that shows the levels, it shows there's our top level, and then everything else is at level 1. And there are a couple other top level ones that function inserted as well. But that's not entirely true, because if you look down here, backpacking has a parent of 19, which is 2-person, which is a parent of 5, which is tents. So you're under this camping 2-person or camping tents 2-person backpacking. So you have this 4 levels of hierarchy, but this query is lying to us because it says they're all at level 1. So we'll go down and try our CTE version of it again and see what we get. And you can see at this point we have level 0, all the top ones, all the stuff at level 1, but now we can see what's at level 2, 3, and 4, and beyond, if there were more. By default, because we haven't specified anything at recursion, this would handle 100 levels of departments. Now I would bet that if you're going to go open your camping and backpacking store, 100 levels of depth is probably enough for whatever you might be selling. But if it's not, you can override that with the max recursion statement. Yes.
What happens when you hit max recursion level? What happens? You said to 3 or something?
I love that question because that takes it right into the next section. Next section here. So let's take a look at the whole sum of parts. So sum of parts of 1 is sum all the numbers from 1 to 1. Well, that's just 1. 2 is 1 plus 2 equals 3. 3 is 1 plus 2 plus 3 equals 6. And you guys get it real quick all the way out to level 10. So what I'm going to do is I'm going to create a function. And in that function, here's how we can do it without a CTE. I'm going to declare a results variable. If the number is greater than 0, meaning we're going to start at a big number, and as we iterate through it, stop at 0 because we've gone all the way from 10, 9, 8, 7, 6, all the way down to 0. And then I'm going to, if it's greater than 0, I'm going to call the function itself. So here's a recursive function, non-CTE. Oops. When we run that, we can then run sum of parts of 10 or sum of parts of 3. We get our 55 or our 6. So yeah, the math looks like it's working correctly there. But what if we want to do sum of parts of 100? Well, here, the maximum recursion you can do in procedures, functions, or triggers is 32. Yeah, most of the time 32 is probably going to be okay. But if you want to go beyond that, here's how we can do it. So we build our anchor query to do our recursive CTE. We select 1 as our count number and 1 as our grand total. So that's our sort of priming the entire thing. Because the sum of parts of 1 is 1. There's our answer for sum of parts of 1. But now we need to build it out further. So we throw it inside of a CTE. You guys can probably imagine what that's going to return. Here's our recursive query, which I forgot to include the from on that part. But here we're going to have our original anchor query, union in it with our recursive query. And the recursive query effectively joins back to everything that's ever returned from the sum of the parts at each level and adds 1 to it as we go through here. And then I'm going to select everything out of that. So when we run that query, oh, what happens when we go too deep on recursion? Crash. The maximum recursion of 100 has been exhausted before statement completion. And technically, the way that this recursive query was built, it's dangerous because there's nothing that ever terminates it. And no matter what level we set it to, it would just keep going until we ran out of memory or decided to go home for the day. And it'd still be running when we came in the next day. But what I'm going to do now is add in this where clause here that says where the count number is less than 10. So don't go any deeper than 10 in this case. When we run that, you can now see we've got a table return that shows sum of parts for 7 is 28, sum of parts for 10 is 55, and you get all the results that way. Now, if we just wanted to look at the max for sum of parts to get similar to our function that we did earlier, where we just want to know it for 10, we can run it this way, and we can now see the sum of parts of 10 is 55. Let's see. Now let's take a look. Well, what happens if we want to go further? Sum of parts of 150. Anybody know that off the top of their head? Well, it crashes. The way we get around that crash is we put in this option of max recursion of 200. Now, you could say option max recursion of 0, which would mean go as deep as you want forever, which would be pretty darn bad if you messed up here. But with this where clause, you would be okay putting a 0 down here. I wouldn't recommend doing it because you could comment that out when you're testing or something and cause problems. So I just threw in a number that was bigger than 150 and gave me plenty of room. I could have used 151 there if I wanted. And when we run that, we can see the sum of parts, 11,325. Is that what you came up with?
Yeah.
Awesome. Wow. That's the first time I've seen someone come up with that. So now, what if we want to go to 4,000 or 40,000? What's the sum of parts of 40,000? Seamus? Anyone? Crash.
800 something.
All right.
800
Wham. It doesn't matter because,
million, 20,000.
all right, 800 million something. So we crash here because the max recursion has gone beyond 32767. But you might think, okay, am I stuck? Can I just not do beyond 32767? No. Wait, hold on. Do I have it down here? Let's get a little bit dangerous. Take a walk on the wild side. And we're going to go with max recursion of 0. But I know that this count number up here is going to terminate it on time. When we run that, 8 million, 800 million, something or other. Wow, impressive. So there are times where it is appropriate to use a max recursion of 0, but you better be very certain that what you've done up here is going to terminate it appropriately. All right, so we're a little bit short on time, so I'm going to jump ahead here to some formatting stuff. So we have this royal family tree that we built out, and if I had another 40 minutes, I'd go through all of this, but it starts out here. We're going to select Prince William as our anchor query. We're then going to select from Prince William his father, his father's father, and fathers all the way up on his father's side of the family. And then for this other recursive query, it's going to select the mother and the mothers of everyone in the tree. We're going to use this, and let me just show you what happens when we run this here. We're going to replicate out with a dot and a few spaces to indent based off of our level. And when we run the whole query, jumping back to recursion here, you can see there's a little bit more effective way. So we can see Prince William is at the top here. His father is there. His mother is here. His mother, they weren't officially royalty, I guess, so they're not quite as much as far back. But there's much more on this side of the family. But if you were building the family tree, it would be much more effective. Oh, I don't have that sample here. There's a way you can do some sorting that will build it out and actually show it where the root node is in the center. All of your father's side of the family is above, or your mother's side of the family is below. And for every individual, you can say the same thing built out that way by doing some sorting with that. So recursive CTEs, there's a bunch of bonus material I've included at the end here out of the book. Fibonacci sequence with recursive CTEs, factorials, some really cool string parsing stuff, more on the royal tree, stuff like that. So on to the quiz part of the class. We've got a few minutes left here. Speak up as we go through these. So a named result set, the CTE is run only once, even if it's referenced multiple times in the query. False. Correct, it is false. It's run once for each time that it's referenced in the query. And if you're joining us online, the timing might not work out right on these, but think about your questions because we'll be answering questions in just a moment. Here's how the explanation of the first one. So in this example where we're selecting this single CTE, it's referenced twice down here, it does get executed twice. And if you take that query and copy it and go look at the plan through this query analyzer, yes, indeed, it will be run twice. That is probably the biggest misunderstanding that people have when they first look at CTEs. They think, wow, I can just go and write this and it gets run once. And in fact, there's a lot of documentation out there on the web where people say it does only get run once. But just look at the plan and you can prove that they're wrong. Okay, CTEs are proprietary to Microsoft SQL Server. I didn't mention this, but anybody know?
No. True.
True? I have one true and one false. False. They're supported on several major platforms, among them PostgreSQL, DB2, Oracle, and SQL Server, and they're as part of the SQL 99 spec. However, when you're working on these other platforms, they're a little bit different. So the syntax is slightly different, and in fact, in some cases, they're even quite a bit different. But you get the same concept out of them. CTEs, this is an easy one. They're a great way to create recursive hierarchical queries. Anyone?
True.
True, yes. I love it with hierarchical queries this way. I used to hate having to deal with hierarchies before this. All right, CTEs are only supported on SQL Server Enterprise 2008 R2 and newer. True or false?
False.
False. They're only available. They are available on 2005 and newer, and on all versions, including SQL Azure. CTEs can be nested, and one CTE can reference an earlier CTE. True or false? Awesome. You guys got it. Indexing CTEs. If you want to make your CTE run faster to boost performance, you can index it.
False.
False. False is correct. It's an inline kind of temporary thing that doesn't exist. You can't index it if there's nothing kept around. Which performs better, a non-recursive CTE or a view?
Same.
Exactly. They are the same. The big gain is when the recursive CTE, which you can't really get with a view. Data paging. CTEs are a great way to do data paging for result grid. Yeah, it depends. Oh, the question was, is that going to be on the test? I don't remember any of the specific questions that were on the 7461 exam, and if I could, I probably shouldn't share them with you. But I do remember the very first question I had on the exam was a CTE question, and I remember there were like 4 or 5 different CTEs on the entire exam. And I took the test right after I finished writing the CTE book, so I was really happy with that. And the test comes from a random bank of questions, so you may not get the same questions when you take it. But I would make sure you know CTEs if you're going to take the test. So SQL Server 2014 and 2012 have the new offset and fetch, which it's easier, but for older versions, CTEs are absolutely the best option. TempDBs. CTEs are similar to temp tables or temp variables in their use of TempDB. I know I didn't cover this much, but anyone know offhand?
False.
False. Why is it false?
Because they're more like code expressions than they are like table groups or something.
That's correct. It's more like how a derived table is stored in the workspace inside a SQL Server rather than in memory, rather than going off to TempDB.
But I did table variables are stored in TempDB.
Table variables and temp tables are both stored in in TempDB. And when I've presented this at SQL Saturdays and other things, some people have jumped up and argued this and said, no, you're wrong. Well, I got tired of that. So I wrote a blog posting that used, it cleared your TempDB log, and then it did each one of these types of queries, and then it showed you how many entries have been written to the TempDB log, and it proved that temp tables and table variables absolutely use TempDB. However, they use them in a different fashion. So they don't use the same amount of space necessarily, and that CTEs do not use TempDB. It's way more time than we have to prove today, but go look at that blog posting if you want to spend, I don't know, 20 minutes of making your brain hurt about how TempDB actually runs. Switching over to Aaron here.
All right. This quiz, intersect can be replaced with which of the following? An update statement, a left join, an inner join, or an inner join with distinct. So you guys think? D? Yeah.
Yeah.
So D?
D, if we had a D.
Yeah, if we had a D.
D4.
Next presentation. Yeah.
Oh,
Yeah. Oh.
wow.
Good job. That's correct. Intersect is the same as inner join with distinct. So now an accept can be replaced with an update, a left join, filtering on null, inner join, or an inner join with distinct.
B.
Which one? The second one?
Yes.
All right. Yep, that is correct. And it is actually better to do that.
Oh, what the heck? Sorry. Sorry.
Hey.
There's worse performance using the intersect over a left join with null than saying there's better performance using the inner join than using the intersect. So although those functions are available, it's better performance using inner join, right? The join syntax. So this question, with tables that have many duplicates, which will return more rows, a union statement or a union all statement? The answer is union all.
B.
Yeah, it does not have a distinct built into it and will return all your duplicate rows.
All right, so at this point, I'm going to open up to any questions on anything we've covered today on set operations, derived tables, common table expressions, and anyone who's watching remotely, feel free to ask at this point. I don't see anything on the...
Due to the 1 minute delay.
Yeah, due to the minute delay, we'll wait a moment here. Anybody in the room have a question?
So on union all, if you know the data is distinct anyhow, is it cheaper to use union all than union? Because then it does, union seems like it has to apply distinct sorting or something to figure it out.
I didn't do performance testing, but I believe from what I read, it was the same performance.
In my experience, union all has generally been faster. But again, it comes back to it depends too on the table size. You might be able to go look and see in certain cases, it doesn't make any difference. In other cases, it makes a huge difference depending on what you're returning or
I just saw that one example where you had the names, Joe, Bob, Bill, or whatever, and you're unioning them.
Yep.
And I wondered if it was cheaper to union all because you know they're distinct already, so you don't have to have it run through the cleanup cycle.
Yep. And I would bet on that exact on that exact query, it wouldn't make a difference. I wouldn't think because it's so darn small. But if it was a much bigger data set, it probably would. But we could just take that and copy it. We can do that offline. Take that and copy it and go look at the plan and see what it actually looks like. And I would bet you that the union has a couple more blocks in there for sorting and filtering that you don't see in the other one. So yeah, good point. Any other questions from anyone, anywhere? All right. For more information, you can visit emergencyreporting.com to find out more about us and why we're doing this. And you can visit Aaron on the web at aaronbooma.com, on Twitter as Aaron D. Booma, or you can visit me on the web at stevestedman.com, on Twitter as SQL EMT. Tune in next week. It's going to be another fun week. We're going to go into derived table queries in way more detail than we did today, looking at correlated subqueries, subquery extensions, any, all, or some, which I bet you most people in the room probably haven't heard of those. And then we're going to take a look at the exists as well as the output clause. Quick show of hands, how many people have used the output clause in SQL Server? I don't see any hands. It is so cool. And I shouldn't get so geeked out like that, but the output clause, it's just so cool when you want to be able to get data out of a query that's not actually doing any output, it's doing input. So we'll take a look at that next week. And that's it. Thanks for joining us.
Let's stay online for a few more minutes. I think the broadcast just got some questions.
Oh, we're that far behind. Okay, that's fine. We'll see if any questions pop up online.
I have a couple PR comments.
Yeah.
All right, so I don't see any other questions coming in at this point. So let me end the broadcast.
One pops up.
Yeah, if you guys